Hi, welcome to a new session of circuits and networks, that is under transient analysis. We are going to see initial conditions of RLC connected in series or in parallel arrangement. This particular class we are going to take as class 6, and this is followed by class 5. So you can go to my previous video for class 5, where we have already seen the RLC connections in series and parallel, and how does the current conditions can be obtained for different passive elements. So in today's class, it is an extension of class 5. We are going to see this problem where you can see the passive elements, that is 0.24 farads, 50 ohms, 4 henries, and the arrangement of switch which is positioned at P as well as in Q. So you can see a switch S is there. What it is indicating? It is indicating that this switch can be moved from P to Q. Okay, so that is how you have to understand the problem. The similar case, you can see the positions of switch 1 and 2 under 110 volts, where the passive elements, they have changed the positions and also the values are changed. We can see here we have 2 henries and here you have 12 millifarads connected in series with 10 ohms. So how to solve these two problems, step by step approach, we are going to see in today's session. Let us go with first problem, where you have a network which is shown in figure 1. The switch is moved from position P to position Q. So initially the switch position was at P, and then it is changed to Q when it is changed at T equal to 0. So it is also given that the steady state conditions have already reached before switching. Means what? When the position of the switch is at point P, the steady state conditions have reached. So we need to understand the basics of steady state conditions for resistor and inductor. Resistance, it doesn't have any impact, whereas the inductor, the behavior during initial conditions and final conditions, it will be different. So the switch condition is at P and then it is changed to Q. So when the position of the switch is at P, 120 volts is connected to 50 ohms, and that is in series with 4 henries inductor, and this position is kept P for assumption for long duration. Means what? The inductor, when it was at position P, it has reached to its final condition. So in final condition, the behavior of the inductor, it becomes short circuit. When it becomes short circuit, it is understood that the inductor is consuming energy. So how to understand this? Step by step you'll see. So the switch is in position P and the steady state conditions is reached. Okay, so this was the prior switching condition. So inductor in steady state, that is at final position, behaves as short circuit. If that is true, we are going to treat this position of P as before switching. So before switching, the T condition is taken as 0 minus. So how does the circuit look like? This is how the circuit looks like. So inductor during steady state behavior, it will be short circuit, and 120 volts is connected to 50 ohms. The switch is closed. In fact, 0.2 farad, it is not connected. So when it is not connected, you can change this circuit to this circuit. So we are treating this circuit as figure 1a, where 120 volts is connected to 50 ohms. Now it's a closed circuit, and I want to know the value of current, that is I of 0 minus current before switching. So apply KVL to this loop, and we are going to get minus 120 plus 50 I of 0 minus is equal to 0, which will give you the value as I of 0 minus, which is equal to 120 by 50. In fact, sorry, 120 by 50, in fact, this becomes 12 by 5, whose value is 2.4 amperes. Now this is the current which is stored in the inductor, and this current will not change instantaneously. Means what? At t equal to 0 plus, immediate after switching, the inductor current will be changed to 2.4 amperes. So I of 0 plus value is nothing but 2.4 amperes. So this is just after switching. This condition of the circuit is just after switching. So position of the switch is moved from P to Q. Here what we have, here we had the capacitor, and capacitor initially acts as short circuit. So when it initially acts as short circuit, naturally we have the closed circuit like this. So at the instant the switch is moved from P to Q, and when you are going to treat that condition as T of 0 plus, it becomes I of 0 plus, which is value is 2.4 amperes. So this is the important case. Now for T greater than 0, so after 0 plus condition, we are treating the condition of the switch for T greater than 0. The present circuit changes to this circuit where you have the capacitor. Now capacitor will come into the picture. Now this circuit is valid for T greater than 0. The circuit is valid for T greater than 0, where you have inductor. Now it is going to dissipate its energy. That is why inductor is shown, which is parallel to 2.4 amperes. You can go through my basics of initial conditions and final conditions for inductor and capacitor from our transient analysis previous classes. So this is how the circuit change. Now we know that the current in inductor is 2.4 amperes. So this will be the at present condition for inductor. Now we have to understand what is this I of t and how to find out this I of t for this closed circuit. Already we know that I of 0 plus is 2.4 amperes. Now here we are going to get the differentiation of current as well as the integration of current, and how we are going to get, we are going to apply KVL. So once we are going to apply KVL, we have to get the voltage across capacitor, voltage across resistor, voltage across inductor, and it is equated to 0. So this is what it is done. You see, the voltage across capacitor is given by 1 by C integral I dt. So that is the voltage across capacitor plus 50I. 50I is the value of the voltage drop in 50 ohms plus L di by dt. In place of L, we have 4 di by dt. It is equal to 0. I hope you understood this equation. Now what we know? We know that exactly at t equal to 0 plus condition, the value of current is 2.4, and the voltage across capacitor, because it is shorted, the value will be 0. So in this equation 3, we are going to apply t equal to 0 plus condition. So this is how the equation will be framed. You have 1 by C, 1 by 2, 0.24, integration 0 to 0 plus I dt. Now this condition is 0. Why? Before and after switching, the voltage across capacitor was 0. That we need to concentrate during this switching action. So this voltage will go to 0 plus 50 I of 0 plus. 50 I of 0 plus, this is nothing but I of 0 plus, the value is 2.4. So 50 multiplied with this will give you the drop across this resistor element, plus 4 di by dt of I of 0 plus equal to 0. Now I want to know di by dt at 0 plus condition. For that, this particular value goes to 0, then I will be left over with 50 multiplied with 2.4 plus 4 di of 0 plus by dt equal to 0. So this one I'm going to treat it as equation 4, and this changes to this. You can see this terminal got vanished. That is the voltage across capacitor at t equal to 0 plus condition, and you have 4 di by dt of 0 plus, which is equal to, you have this 50 I of 0 plus, that is 50 multiplied with 2.4 goes to the next side of the equation and becomes minus 50 times 2.4. Now with this, I'm going to get di by dt of 0 plus, which is equal to minus 50 multiplied with 2.4 divided by 4. So this value will be obtained as minus 30 amperes per second. Now this is the velocity of the current, and that is why the units are amperes per second. Wherever you have di by dt, you will be having ampere per second. So this we are treating as equation 5. Now we need to know also the value of d square I by dt square. So d square I by dt square can be framed with equation 3. How? This is the equation 3. Okay. Now differentiate equation 3 with respect to t. What we are going to get? We are going to get say differentiation of integration will give you the value as I by 0.24. This is the first parameter of this equation. Then 50 di by dt, here you have I, so it becomes di by dt, plus 4 d square I by dt square, which is equal to 0. Now this becomes the standard equation, so we are treating as equation 6. What we need to know? We need to know the value of d square I by dt square at I of 0 plus. So for that I am rearranging this equation as 4 d square I by dt square is equal to minus 50 di by dt and minus I by 0.24. With this, the equation is framed as d square I by dt square, which is equal to minus 50 by 4 di by dt minus I by 4 multiplied to 0.24. Now at t equal to 0 plus, this equation 7 is framed. Now wherever you have the known parameters, that is I know that I of 0 plus value, I know di by dt of I of 0 plus value. So from equation 5 I know that this di by dt of I of 0 plus is equal to minus 30 amperes per second. And from equation 2 we have framed I of 0 plus is equal to 2.4 amperes. Now just substitute the value of equation 2 and equation 5 in equation 7. Then we are going to get minus 50 by 4. Here di by dt value is minus 30. So minus 30 minus you have I of 0 plus, which is 2.4. So 2.4 divided by 4 times 0.24. So mathematical calculation will be giving you the value as 375. That is this value minus 2.5. So 2.4 divided by 4 into 0.24 will give you the value as 2.5. So with this we are going to get the value of current, that is the acceleration of the current, that is 372.5 amperes per second square. So this is how we solve the inductor capacitor problems, the switching conditions, especially when they are changed from one position to another position. In order to get a better idea, let us take example 2, where you have the change position of inductor and capacitor. So in the previous problem, inductor was placed here, that is in series with 50 ohms. Now 10 ohms is in series with 12 millifarad, and inductor it is situated to second position. Now what we need to find out the value of current, then differentiation of current, and then double differentiation of current at t equal to 0 plus. So step by step we'll follow. So first we have to assume that the current the current conditions when the switching position is placed to 1, and at t equal to 0 the switching position is changed to 2. So before switching what is the condition, after switching what is the condition. So before switching the steady state conditions are breached and capacitor in steady state behaves as open circuit. So this is very important factor. Capacitor in steady state behaves as open circuit. So this capacitor is going to get open circuited when the position of the switch was at position 1 and when the steady state conditions have reached. So at t equal to 0 minus, that is before switching, t equal to 0 minus, we are taking this condition, and this is how the circuit looks like. So as stated, capacitor in steady state behaves as open circuit. So this is open circuited. Anyhow, inductor is not connected. So this circuit changes to this circuit. The circuit shown in figure 2a is the open circuited, and when it is open circuited, naturally the current value will be 0. So the I of 0 minus is 0 amperes. So I of 0 minus is 0 amperes because it's open circuit, current doesn't flow in open circuit. But voltage is present. What is the voltage? When you take a multimeter or a voltmeter, connect to these two terminals of 10 ohms and ground connection, you are going to receive what energy? The energy which is being supplied, that is 110 volts. It is showing the voltage of this particular source, that is why it is 110 volts. So V of 0 minus is equal to 110 volts. This we need to keep in our mind. So thus we are treating this equation as 1. And we have to also understand the behavior of the capacitor, that the voltage across the capacitor cannot change instantaneously. And since V of 0 minus is 110 volts, it is obvious that at t equal to 0 plus, when the circuit is changed to this, the current is 0 amperes and the voltage is 110 volts, and switching position is moved from 1 to 2. When the switching position is moved from 1 to 2, the current is already 0. The current is already 0, but you have the voltage. The current is already 0, so that's why I of 0 plus is 0 amperes, but voltage is present. So voltage is present, so current remains 0, and voltage when it is present, it is showing as 110 volts. Now this is the voltage developed in the capacitor. So that voltage should be kept in series with the capacitor. Unlike the previous condition, we have kept current source parallel to inductor. You can check in the previous problem. The current was kept parallel to inductor. Here voltage should be kept in series with capacitor for t greater than 0 conditions. So how this figure 2b will change to 2c, you will see here. See, inductor has come into the picture for t greater than 0, where we need to find out the value of di by dt and d square I by dt square. So the closed circuit will be found when the position is moved from 1 to 2. So as I told you, since it's a capacitor, that's why voltage developed in the capacitor is kept in series. Now this is the closed circuit. Now in this, we need to find out the conditions for velocity of current as well as the acceleration of current. So for t greater than 0, the circuit is already framed. Apply KVL. So there is a voltage drop in inductor, there is a voltage drop in resistor. You have voltage source 110 volts and you have 12 millifarads. So you can see L di by dt is the voltage drop. So L is 2 di by dt. This is one drop. Then you have 10 multiplied with I, 10i. Then you have 110 volts. So 110 volts plus 1 by c integral I dt. So 1 by c is 12 millifarads integral I dt. I hope you understood this equation 3. Very simple. Just apply KVL and you have to take the sum of the voltages in a closed circuit and make it equal to 0, satisfying Kirchhoff's voltage law. What we need to know, di by dt as well as d square I by dt square. For t greater than 0 conditions, we have framed this equation, and from here we need to find out di by dt of I of 0 plus. So 2 times di by dt of 0 plus 10 multiplied with I of 0 plus 110 plus 1 by 12 millifarads. The position of the switch is moved from 0 to 0 plus IDD equal to 0. So what are the parameters which gets eliminated? We have I of 0 plus is equal to 0, and you have 0 to 0 plus, the voltage across capacitor is 0. So naturally from this main equation we are going to apply the values of I of 0 plus and the switching from 0 to 0 plus. So this parameter and this parameter will go off, hence we are going to remain with 2 di by dt of I of 0 plus, which is equal to minus 110. In fact, divide this 2 divide 110 by 2, so it becomes di by dt of I of 0 plus, which is equal to minus 55 amperes per second. So this is how the value of current is obtained in terms of its velocity. Now once we are framed with the velocity of the current, let us go with the acceleration of the current. For that we need to take again equation 3. This is the equation 3. Already we have derived this equation. Now we need to know d square I by dt square. So what I'm going to do, I'm going to differentiate this equation with respect to t one more time. So this becomes 2 d square I by dt square of I plus 10 di by dt. Differentiation you have for the constant as 0, and differentiation of integration will give you the value as I by C, whose value is 12 millifarad. Okay, now we need to know the value of d square I by dt square at I of 0 plus. So I of 0 plus, the values are substituted as it is, and wherever you have the di by dt value of I of 0 plus and I of 0 plus value, just substitute the value in order to get the d square I by dt square of I of 0 plus value. So we know that from equation 2 the current value is 0, and from equation 4 we got the value of di by dt of I of 0 plus is equal to minus 55 amperes per second. Just substitute the value in equation 6. So I'm substituting these two values 4 and 2 in equation 6. So 2 d square I by dt square I of 0 plus 10 times minus 55 plus 0 this value plus the 0 of the current which is placed over here. So with this we are going to get the d square I by dt square of I of 0 plus, which is equal to minus 10 by 2 times minus 55, and anyhow these parameters goes to 0. So this particular calculation will give you the value as 275 amperes per second square. So this we are going to treat as amperes per second square because it's a value of acceleration. So that is why amperes per second square, acceleration of current. So this is how we solve this kind of problems. In class 5, resistors are used for inductor and capacitor, and in this particular case, that is in class 6, how it is different. Instead of resistor at position Q and position 2, we have taken passive elements as 0.24 farads and 2 henries, and we have tried to understand the behavior of transient analysis in terms of initial conditions. So I hope you like my video. Please share among your friends, subscribe to my channel, and please press the bell icon for future notifications. Thank you.